Okay, students. So today we are going to start with A2 Physics topical past papers for the chapter of electromagnetism. This is your chapter number 9. This is your chapter number 9. Okay. And don't worry about this PDF. This PDF, along with all the topical past papers for A2, are attached in the description below. And a unique thing about this PDF is that you have the marking schemes directly attached with the questions. Okay. So let's move on to the first question. What is the first question? State Faraday's law of electromagnetic induction. Yes, what was Faraday's law of electromagnetic induction? Induced EMF is directly directly proportional to what? Is directly proportional to the rate of change of magnetic flux. Induced EMF is directly proportional to the rate of change of magnetic flux. Let's further move ahead. Figure 7.1 shows a coil at rest, okay, in a uniform magnetic field that is parallel to the axis of the coil, okay. The coil is connected to a center 0 voltmeter, okay. The flux density of the uniform magnetic field varies with time as shown in figure 7.2, okay. So this magnetic field's flux density is varying with time like this, okay. The coil consists of 340 turns, okay. Each has a cross section area of 3.2 into 10 raised to the power of minus 4, okay. Calculate the maximum. You have to calculate the maximum magnetic flux through one turn. You have to calculate the phi maximum, okay. How will you calculate that? By putting in the maximum magnetic flux density multiplied by the area. Now, if I go to the graph, my maximum magnetic flux density is this point. This point. Now, how to calculate this point? Let's zoom in a bit. Let's zoom in a bit. 1 second. Yeah. Here, if you can see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are 10 boxes and you are jumping from 4 to 8. So 10 boxes cover how many units? 4 units. One box will cover how many units? 0.4 units. So basically, how many units apart is this? 1, 2, 3, 4, 5, 6, 7, 8. Okay, 8 units. So 8 into 0.4, that is equals to 3.2. 4 plus 3.2 is equals to 7.2. So your maximum magnetic flux density, this point is 7.2 millitesla. So let's write it here. Let's write it here. 7.2 into 10 raised to the power of minus 3. And what is your area? What was your area? 3.2 into 10 raised to the power of minus 4. 3.2 into 10 raised to the power of minus 4. You can calculate the answer using a calculator. Let's do it. 7.2 into 10 raised to the power of minus 3 multiplied by 3.2 into 10 raised to the power of minus 4. This comes out to be 2.3 into 10 raised to the power of minus 6 Webers. Now, one thing you might have noticed that I have not multiplied this 340 turns. Why? Because we had to calculate the magnetic flux for only one turn. We had to calculate the magnetic flux for only one turn. So let's further move ahead. Determine the maximum rate of change of magnetic flux linkage. Okay. So basically we have to determine what? We have to determine change in phi over change in t ki maximum value. We have to determine this. Okay, so basically I can't directly determine this. I can't directly determine this because I'm not given anything like this to determine the maximum value of change in magnetic flux over time. What I can instead do is I can divide this fraction. I can break this fraction down into something like this. We know that phi is equals to what? NBA. Okay, so let's write it here. N and area wouldn't change. Okay. B can change. Okay, so change in B over change in time. is equals to. Now move the NA outside the bracket. Why? Because NA wouldn't change. The only thing that is changing here is your magnetic flux density. Now this seems a more reasonable approach. You have your N, that is 340, you have your area. Can you calculate the maximum value of change in B over change in T? Yes, you can do that. How will you do that? You will go to the graph and see for the maximum gradient here. The gradient, if you observe closely, the gradient of this graph is what? Change in B over change in T. You have to calculate the maximum gradient on this graph. And then you will get your maximum change in B over change in T. So let's do that. I think here at point 0, if I draw a tangent here, my gradient will be maximum. Let me make the tangent correctly. Somewhat like this seems, oh, something like, yeah, this seems perfect. 1 second. Let me adjust it thoda sa downwards. 1 second. Yeah, a tangent like this will do the job. Obviously, this is a digital thing, so you can make a tangent more clearly than me. So, yeah. Now we have 2 points on this tangent. Let me take the 2 points. We have 1 point as roughly this, that is equals to 0.4 on the x-axis and 4 on the y-axis, and then we have this point that is 0 on the x-axis and 1 on the y-axis. Okay, can I calculate the gradient here? Yes, gradient is equals to y2 minus y1, 4 minus 1, x2 minus x1, 0.4 minus 0. This comes out to be 3 divided by 0.4, that is roughly equals to 7.5. Now you might have noticed that I haven't taken the units of the axes. Both axes are in milli, 10 raised to the power of minus 3 and 10 raised to the power of minus 3. So both of them will get cancelled out. Like let's say if I put units here, 10 raised to the power of minus 3 and 10 raised to the power of minus 3, both of them will cancel out. So I haven't put the units here. So let's further move ahead. Your gradient comes out to be 7.5. This is the maximum value of gradient. Okay, let's put it here now. What was your value of n? Your value of n was 340. Okay, let's put 340 here. What was your value of area? What was your value of area? 3.2 into 10 raised to the power of minus 4. 3.2 into 10 raised to the power of minus 4. What was your maximum value? 7.5. Calculate the answer. 340 into 7.5 into 3.2 into 10 raised to the power of minus 4 into 7.5. This comes out to be 0.82. This comes out to be 0.82 Webers per second. Okay, let's further move ahead. State the maximum electromotive force induced across the coil. So if you are a good student, you might remember that EMF was equals to what? Change in phi over change in time. Now, if this value is maximum, induced EMF will be maximum. So what was the maximum value of change in phi over change in time? 0.82. So the maximum value of EMF will also be 0.82. Simple as that. On figure 7.3, sketch the variation of the induced EMF across the coil from time t is equals to 0 till time t is equals to. Okay, so this is a tricky question. Let's see it a bit. You have to draw the induced EMF graph from time t is equals to 0 till time t is equals to 6 millisecond. Okay. So let's write the induced EMF formula. Induced EMF used to be equal to change in phi over change in time. I can break this formula like this: NA into change in B over change in T. Okay. And I also know that n, that is the number of turns, and a, that is the area, is going to remain constant throughout. The only thing that changes is change in B over change in T. Okay. Now let's move on to the graph above for B versus time. This is a graph for magnetic flux density versus time. Okay. If you see at time t is equals to 0, if you see at time t is equals to 0, if I draw a tangent here, if I draw a tangent here, what will happen? 1 second. Let me do it like this. If I draw a tangent here, this is a horizontal line. This is a horizontal line. Hence, change in B over change in T will become what? 0. Horizontal lines have a gradient of what? 0. Hence, at time t is equals to 0, your induced EMF will become 0. Why? Because this change in B over change in time has become 0. So let's place a point 0 here. Okay. Then let's come on to time t is equals to 1. Again, at time t is equals to 1, what is happening? If you see at time t is equals to 1, if I draw a tangent here, again, at time t is equals to 1, again, I have a horizontal line here. Gradient will be 0, change in B over change in T will be 0. Again, my induced EMF will be 0 at time T is equals to 1. Okay, let's place 0 here. Let's see what happens at time T is equals to 2. At time T is equals to 2, if I try and minimize this, you will be able to see it. Okay, some things haven't copied. So let's write it here, horizontal line. Now let's draw a tangent again at time t is equals to 2. Again, you will notice that this is a horizontal line. Horizontal lines have a gradient of 0. Change in B over change in T will become 0. So at time t is equals to 2 as well, your potential induced EMF is 0. Let's check out at 3 seconds. At 3 seconds, it is also 0. At 4, it is also 0. At 5, it is also 0. Okay, so let's mark the zeros correctly first of all. 3, baby, your induced EMF is 0. At 4, it is 0. At 5, it is 0. Okay, now you have more than enough points. More than enough points. What was your maximum induced EMF? 0.82. Okay, so let's locate 0.82. This will be somewhere your maximum induced. Okay, I think the examiner has already told us that this point is your maximum EMF. Okay, so you will reach a maximum EMF in the middle. Something like this. Something like this. If you are good at maths, you will start to know which type of a graph is this. Something like this. The examiner had already marked हमारे लिए maximum and minimum EMFs. So I didn't locate at the point. Something like this. I guess this will be enough. This is your graph. Now, one question that might come in your mind again is, sir, why didn't you mark 0.82 here as your maximum EMF and then draw the graph? Because beta, the examiner has already marked the maximum EMF for me. He has already pointed out where will the maximum EMF be with the V naught and negative V naught values. So if the examiner has already located the maximum values of EMF, you don't need to be over smart and relocate them. The variation of voltage with time t can be described by this equation, okay, where A and B are constant. Now we have studied this where? In chapter number 10, alternating currents. Okay. What is A? A is your amplitude. Amplitude is what? Maximum voltage. What will be the maximum voltage or EMF in this graph? 0.82. What will be the units? Volts. What will be the value of B? Yes. Does anyone remember what was B? B used to be RW. How do we calculate W? 2 pi f. Do we have the frequency here? Let's check out. Do we have the frequency here? No, we don't have the frequency throughout. But instead, we have one more thing. Can you see this entire wave is getting completed in how many seconds? 2 milliseconds. So I can employ another formula for W. I can say W is equals to 2 pi over T. Okay. B is equals to what? 2 pi over the time period, that is 2 into 10 raised to the power of minus 3. Let's calculate this. 2 pi divided by 2 into 10 raised to the power of minus 3. This comes out to be round about 3141. Okay. And what will be the units here? 3141 seconds minus 1. Simple as that. And if you are a very good student, you will follow exam conventions and give it till three significant figures. So these are your answers. Let's check out the marking scheme as well. Yes, as you can see here, the answers are pretty similar. Here the examiner has given the answers to two significant figures. It doesn't matter, either you give your answer to two significant figures or three significant figures. Chalo, let's move on to the next question. An object travels in a circle at constant speed. State the name of two quantities that vary during the motion of the object. The first quantity that varies is the velocity, because as your direction is changing, your velocity is changing. Secondly, you can say acceleration also changes. Acceleration also changes. Now let's further move ahead. A charged particle of mass m with a charge q enters a region of uniform magnetic field, okay, perpendicular to the field lines. The magnetic flux density is B, okay. The particle travels in a circle with a period of t and a radius of r, okay. By considering the magnetic forces acting on the particle, show that this. Okay, so first of all, let me draw a diagram here. Let's say this is a magnetic field. Although diagrams are not necessary, I am just drawing it for you to get a better understanding. Let's say this is a charged particle entering the magnetic field like this. And due to the magnetic field, this charged particle will start to deflect in a circle like this. Okay, let's say this is a charged particle of positive Q. Now, whenever a charged particle enters a magnetic field, a magnetic force acts like this on the charged particle. Let's say this is your magnetic force. Similarly, a centripetal force acts away like this as well. Okay, so what can you say here? You can say that centripetal force will be equal to the force of magnetic. Sorry, I have written G here. I don't know why. This will be Fm. Fm. Okay. What is the formula for centripetal force? Does anyone remember? mv square over r. What was the formula for magnetic force on a charged particle? BQV. V and V get cancelled out. Let's make charge the subject here. Let's make B the subject here. Okay, we have to make B the subject. So B is equals to mv over rq. Still, if I see my question, I am not getting the similar form. Still, if I see the question, I am not getting the exact same form. What will I do? I will try and substitute out this value, because velocity is not seen in this entire equation. So I remember that velocity is equals to what? RW. And W is equals to what? 2 pi over T. Velocity will be equal to 2 pi R over T. Let's substitute it here. B is equals to what? M into 2 pi R over T multiplied by RQ. This R and R will get cancelled out. The remaining will be 2 pi M divided by QT. This is your same as in the question. The particle is an alpha particle. Okay, the particle is an alpha particle. The period of the circular motion is this. Calculate B. We have to calculate B. How will we do that? What is the formula for B? B is equals to 2 pi M over qt. Okay, what is the mass of an alpha particle? Yes, can anyone tell me what is the mass of an alpha particle? 4 into 1.66 into 10 raised to the power of minus 27. What is the charge of an alpha particle? 1.6 into 10 raised to the power of minus 19 into 2, because an alpha particle contains two positive charges. And what is the time? What is the time period here? 2.5 microseconds. 2.5 into 10 raised to the power of minus 6. What will be your answer for B? Yes, what will be your answer for magnetic flux density or B? Can anyone calculate it? The answer for B comes out to be 0.052. 0.052 Tesla. Okay, let's see part 3. A second alpha particle is in the same uniform field. It travels in a circle of radius 2r. Okay, so now the radius has doubled. Okay. State and explain how the period of the motion of the two alpha particles compare. Let's see. We have to compare time. So let's take this equation here. Let's do this working. B is equals to 2 pi m over qt. Let's make t the subject here. T is equals to 2 pi m over qb. Now, if you can notice in this formula for time, there is no radius ka component. In this entire formula of time, time is dependent on mass, charge, and magnetic flux density, but not on radius. So, what will you say? Time, period, and radius are independent of each other. Are independent of each other. Independent of each other. Hence, time period remains constant. Yeah, same. You can say same as well. Time period remains same. Simple as that. Let's further move ahead. Let's see part 4. The speed of alpha particles in B2 is 1.11 into 10 raised to the power of 6 ms minus 1. Okay. An electric field is applied so that the particles now move with constant velocity. Okay. Use your answer in B2 to calculate the electric field strength given the unit. Give the unit with your answer. Okay. So basically now what will happen? Your force of electric will be equal to your magnetic force. Okay. Because now there is no circular motion being performed. So what was the formula for electric force? Does anyone remember what was the formula for electric force? Electric field strength into charge. Okay. What was the formula for magnetic force? BQV. Is there anything that is cancelling out? Q and Q gets cancelled out. Okay. You have to calculate the value of E. Okay. E is equals to BV. What was your B coming out to be? B was coming out to be 0.052 Tesla. So let's place it here 0.052 Tesla. What is the velocity here? 1.1 into 10 raised to the power of 6. 1.1 into 10 raised to the power of 6. What does your electric field ka answer come out to be? Your electric field ka answer comes out to be 5.7 into 10 raised to the power of 4. 5.7 into 10 raised to the power of 4. Units can be Newton Coulomb minus 1. Simple as that. Units can be Newton Coulomb minus 1. Let's further move ahead. Obviously, you can check with the marking scheme. A small coil C, okay, has 64 turns, okay, and the cross sectional area is 0.7 centimeter square, okay. This is your coil C, and this has the area of 0.71 centimeter square, 64 tons. Okay. The coil is placed inside a solenoid as shown in figure 6.1. Okay, this coil is placed inside a solenoid as shown in figure 6.1. Okay. The center of the coil is on the central axis of the solenoid. Okay, that's perfect as well. There is a constant current in the solenoid. Okay, there is a constant current in the solenoid. Okay. Coil C is moved through the solenoid from point X to Y. Okay, it is moved from point X towards Y. Okay, On figure 6.2, sketch a line to show the variation of the magnetic flux linkage. You have to tell how phi will vary as the position shifts from x to y. Okay. So one thing to remember for examination is that phi can be represented as magnetic flux linkage or magnetic flux. Both of these words will be interchangeably used for phi in your examinations. Okay. Let's see how will we draw magnetic flux linkage versus distance ka graph. So what do you think should happen? What do you guys think should happen here? Yes, any ideas, any suggestions in the chat or in the comments? I am leaving you guys for 1 minute to think about it. Yes, what will happen to your magnetic flux linkage ka graph throughout x to y? Yes. So if you think about it, your magnetic flux linkage phi is equals to B into A. Okay. Your magnetic flux linkage is equals to B into A. As you move from X to Y, the magnetic flux density B at X and B at Y will remain same and the area is also same. So the if both these things remain constant, this also remains constant as you move from X to Y and this also remains constant as you move from X to Y. What will happen to your magnetic flux linkage? It will also remain constant. It will be a straight horizontal line. Like this, I hope I have drawn it as a horizontal line. Let's do part 2. Explain the shape of your line in part A. So that's very easy. We know that phi is equals to B into A. And as B at X is equals to B at Y and as A at X is equals to A at Y, the phi at X hence will be equal to phi at Y. Simple as that. Let's further move ahead. Coil C is now held stationary at point X. Okay. The current in the solenoid varies, so the magnetic flux density B at X varies from time t is equals to 0 to time 40. Okay. So from time 0 till 40, this is the variation of B versus time. Okay. Calculate the maximum magnetic flux linkage. Again, similar type of questions to what we have done in question 1. You have to calculate maximum magnetic flux. Maximum magnetic flux will be equal to what? Maximum value of B into area. What is the maximum value of B? The maximum value of B is 0.08 here. Okay, so let's place it here. 0.08. What is the area? What is the area? Let's see. We did have the area, right? Yeah, we have the area as well and we have the number of turns as well. Area is 0.71. The number of turns is 64. So as you can see here, we have to calculate it for the entire coil. So this formula will change slightly and we will multiply it by n as well. Okay? If it was for one turn, I wouldn't have multiplied it by n. But since it is for the entire coil, I will also have to multiply it with n. What are the number of turns? 64. Area is 0.71. 64 into 0.71 and the 0.71 is in centimeter square. This is also a problem. You will have to convert it into meter square. This is in centimeter square. You will have to convert it into meter square. To convert centimeter square into meter square, what do? You multiply it by 10 raised to the power of minus 4. So 10 raised to the power of minus 4. So you multiply it. What does your answer come out to be? Yes, anyone. The answer comes out to be 3.6 into 10 raised to the power of minus 4 Webers. Simple as that. Let's do part 4. On figure 6.4, sketch a line to show the induced electromotive force in coil C from time t is equals to 0 till time t is equals to 40. So basically now you have to draw the graph of induced EMF E. So as we know, EMF is equals to what? Change in phi over change in t. Okay. This change in phi can be broken down into what? NA into change in B over change in t. Okay. So let's draw a graph. From 0 till time t, can you see this graph, change in B over change in T is equals to 0. Hence your EMF will also be equal to 0. Let's make a blue line here. I am doing it with the blue because the rest of the working is done with red, so to create a distinction. So from 0 till time t, you will have a 0 EMF. Why? Because your change in B over change in T is equals to 0. This causes the entire EMF to be 0. Then from T till 2T, from T till 2T, you have a positive gradient. Can you see? One second, let me take a highlighter. This change in B over change in T is positive. Okay, so you will have a positive EMF. Let's make a positive EMF here. Let's say you have a positive EMF like this. Something along these lines. And let's complete this graph by drawing vertical lines as well. इस तरह से. Something like this. And like this. Obviously, my drawing is worse than a grade 1 student, so these might not even look vertical. But remember, these lines are vertical, okay? So now from 2t till 4t, you have a negative gradient. You have a negative gradient like this. This is your negative gradient. Change in B over change in T is negative. Okay. So your EMF will also be negative. Let's draw it as well. Something like this. Oh, I hate my drawing. Literally, this is the worst thing to happen to humanity. So, yeah. Something like this. Okay, let's further move ahead. A metal spring rests on a smooth table. The turns of a spring are equally spaced. The ends of the springs are connected to a DC power supply as shown in figure 6.1. Okay. The spring is connected to DC power supply using flexible leads. Okay. The spring is not under tension. Okay. With reference to magnetic fields, describe and explain the change in the distance between the turns of the coils of the spring when the power supply is switched on. So basically you have to tell how will this distance x between these coils vary as soon as you switch on the current. As soon as you switch on the current, how will this distance vary? So let's answer this. How many marks does this question carry? 3 marks. Okay, so we will have to answer carefully. Okay, so basically, as you connect it to a DC supply, what will happen? A current will start to flow through these entire coil. A current will start to flow through this entire coil. Let's first of all visualize it. What will happen? Let me take this, these two, what you can say, turns of a coil. Let's take these two turns of a coil. Let's make it dotted so that you know what I am drawing. Okay, let's take these two turns of the coil. Let's say this is the first turn of the coil, turn 1, and let's say this is the second turn of the coil, let's say turn 2. Now, as soon as current goes into this coil, what will happen? As soon as current goes into this coil, it will generate its magnetic field. It will generate its magnetic field like this. Okay. And when the current will go into this turn 2, when the current will go into this turn 2, what will happen? This current in turn 2 will interact with this magnetic field of current 1. You can write it here. The current in turn 2, yeah, in wire 1, yeah, in wire 2. You can say the current in wire. Oh, better word would be to visualize it like this. Let's say this is wire 1 and let's say this is wire 2. See what has happened. Wire 1, the current has passed through wire 1. It has given rise to magnetic fields. When the current passes through wire 2, the current in this wire interacts with the magnetic field of wire 1. Let's write it down so that it becomes more clear in your head. Current in wire 2 interacts with the magnetic field due to magnetic field due to wire 1. Okay. So current in wire 2 is interacting with the magnetic field due to wire 1. When this happens, an attractive force is produced like this. When this happens, an attractive force is produced like this. Why does an attractive force gets produced and why not an repulsive force? Because both the currents are in the same direction, hence an attractive force gets produced. So how will you write this answer? How will you write this answer? You will say current in the you can say coil gives rise to current in the coil gives rise to what? Current in the coil, or you can say spring, creates magnetic field. Creates magnetic field. Simple as that. Now what will be your second step? Second step में क्या कहोगे? Current in current in one turn, or you can say wire 1, obviously it is your choice. Current in one turn interacts with the magnetic field created created by the current magnetic field created by the current in another turn. You can write it like this: in an other turn. In an other turn, or you can further rephrase it like this: in the corresponding turn. Current in one turn interacts with the magnetic field created by the current in the corresponding turn. This gives rise to an attractive force. This gives rise to an attractive force. And due to an attractive force, what will happen? This gives rise to an attractive force, and we had to specify, right, with reference to decide the change in distance and the distance between between the turns between the turns decreases. Simple as that. Okay, let's move on to the next question. This was a good question. You can see similar things are written here. Let's move on to this question. A Hall probe containing a thin slice of semiconducting material is placed in a uniform magnetic field of flux density B. Okay. The largest faces of the slice are perpendicular to the magnetic field as shown in figure 7.1. Okay. Let's see what is written ahead. The thickness x of the slice is this. The number density of charge carriers in the semiconducting material is this. Okay. A constant current is flowing. Okay. The hole's voltage VH that developed between terminals P and Q is recorded. Okay. Show that when B is equals to this value, your hole's voltage is equals to this value. So what was the formula for hole's voltage? Do you remember? Hole's voltage का formula क्या था? BI over NTQ. So what is your B here? 4 into 10 is the power of minus 6. What is your current? Your current is 5.4. Okay, let's multiply it by 5.4. What is your number density of charge carriers? 1.5 into 10 raised to the power of 16. 1.5 into 10 raised to the power of 16. What is your thickness here? 1.8 millimeter. 1.8 into 10 raised to the power of minus 3. What is the charge Q? 1.6 into 10 raised to the power of minus 19. Can you calculate the hole's voltage for me? Can anyone calculate the hole's voltage? The hole's voltage ki value comes out to be what? 5 volts. Simple as that. Now let's move on to part 2. On figure 7.3, sketch the variation of Hole's voltage with time t between time t is equals to 0 till time t is equals to 0.08 seconds. Okay, so we have to draw the graph for Hole's voltage. Let's see this. As you can see, B is starting from 0 at time t is equals to 0. So Hole's voltage will also start from 0 at time t is equals to 0. And at time t is equals to 0.02, B reaches a value of 4 into 10 raised to the power of minus 6. So at 0.02 seconds, Hole's voltage will be 5 volts. Let's first of all draw for this slanted line. Let's first of all draw this slanted line on the Hole's voltage graph. At 0, you have a Hole's voltage of 0, and at 0.02 seconds, you have a Hole's voltage of 5, somewhere here. Let's draw a slanted line like this. First of all, like this. Okay. Now let's further move ahead. Now let's see the second part of this question. Let's see the second part of this question. For the second part of this question, you are going from 0.02 till 0.04. Okay. You have a constant B. If you have a constant B, your whole voltage will remain at 5. Okay, your whole voltage will remain at 5 volts. So let's keep it till 5 volts for 0.02 till 0.04. Something like this. Like this. And obviously, this is again a digital drawing. So maybe some ticks are off the marks. Now from 0.04 till 0.05. Again, let's highlight this in green. This line, in this line, what is happening? Your whole voltage is decreasing. Okay, but how much? How will I get to know the value of the new hole's voltage? If you see, this B value has halved. Initially, this B value was 4. Now it is 2. This B value has halved. What will happen to the hole's voltage? If B has halved, what will happen to the hole's voltage? It will half as well. So from 5, it will drop down to 2.5. From 0.04 till 0.05, your whole voltage will come towards somewhere here, 2.5. Somewhere here, yeah, 2.5. Let's draw a line here, something like this. Something like this. Obviously, again, pardon me if I do 1 to 2 boxes above below because really bad at drawings. So now from 0.05 till 0.08, you have a constant holes voltage because your B is getting constant at 2 into 10 raised to the power of minus 6. Let's see. Let's see. Let's draw it. Let's draw it like this. Somewhat like this. It will be a horizontal line. Okay. So something like this. Something along these lines. Yeah. So this is how your whole voltage graph will be. This is how you will get a 3 on 3. Let's further move ahead. The whole probe in A is replaced with a small flat coil that has 3000 turns. Okay, now you have 3000 turns. The cross sectional area of the coil is this. You have the area as well now. The plane of the coil is perpendicular to the magnetic field. The electromotive force induced between the terminals of the coil is recorded as B varies as shown in figure 7.2. Okay. So basically EMF is recorded as B varies. Okay. Show that the magnitude E of the EMF at time t is equals to 0.01 seconds is 2 into 10 raised to the power of minus 4 volts. Okay. So EMF is basically equals to what? Change in phi over change in time. How can I represent phi? NA into change in B over change in T. What is the number of turns? 300. Oh, sorry, 3000. What is your area? 3.4 into 10 is the power of minus 4. And what is your change in B over change in T? At time T is equals to 0.01 seconds. Let's see. Let's find out. We have the graph for that. Let's erase all these colors. Okay. At 0.01 seconds, somewhere here. Okay. What will be your gradient here? Because you have to calculate the change in B over change in T at 0.01 seconds. So you can take 2 points here. Let's say this is 0, 0, and let's say this is x 0.01 and y 2. So what will we do? How will we calculate the gradient? Y2 minus y1, 2 divided by x2 minus x1, that is 0.01. And are there any prefixes that we are missing? Yes, 10 raised to the power 6 is missed here. So let's calculate this gradient. 2 into 10 raised to the power of minus 6 divided by 0.01. This comes out to be 2 into 10 raised to the power of 4. 2 into 10 raised to the power of minus 4. This is your gradient. Okay. Let's plug it in here. Let's plug it in here. 2 into 10 raised to the power of minus 4. Okay. Let's multiply all these values and let's see what our answer comes out to be. Answer multiplied by 3000. Okay. Multiplied by 3.4 into 10 raised to the power of minus 4. This comes out to be 2.04 into 10 raised to the power of minus 4 volts. That is roughly equal to 2.0 into 10 raised to the power of minus 4 volts. Let's move on to the next part. On figure 7.4, sketch the variation of E. Basically, we have to sketch the variation of EMF with time t between t is equal to 0 till t is equal to 0.08 seconds. Okay, you have to sketch the graph of EMF from time t is equal to 0 till time t is equal to 0.08 seconds. Okay, so how will you do that? First of all, go to this graph. Let's erase this completely. Okay, from 0 till 0.02 seconds, from 0 till 0.02 seconds, there is a positive gradient. Your change in B over change in T is positive. So basically your EMF will be what? Your EMF will be positive as well. And what will be your value of EMF at 0.02? It will be something like this. Now you will ask, sir, how did you know we will draw a horizontal line like this? Because I just have applied a very recurring formula. EMF is equals to NA into change in B over change in T. Now I know change in B over change in T is positive. So the value will be in the positive y-axis. Secondly, I know that I have calculated this value in the previous part I1. So from 0 till 0.02, your EMF will be 2 into 10 is the power of minus 4. Okay, from 0 till 0.04, 0.02 till 0.04, what do you see? Your gradient change in B over change in T is 0. What will happen to your EMF? It will drop towards 0. Something like this. I know this is a difficult chapter, but I am trying to make it as easy as possible. If you still have any confusion, you can obviously ask in the comments. Now, from 0.04 till 0.05, can you observe a thing? From 0.04 till 0.05, that is somewhere here. You have a change in B over change in T as negative. Okay, so what will happen? Your EMF will be negative. So let's draw a negative EMF of the same value. Now, an intelligent student will ask, sir, why have you drawn it of the same value? Why have you specifically chosen minus 2 as your negative EMF and not any other value? So that's a very good question. Why have I chosen negative 2 as my voltage ki value, EMF ki value here? Because if you see here, both of these gradients, this one 1 and 3, the gradients at line 1 and 3 are equal in magnitude, but they are opposite in signs. They are equal in magnitude, they are opposite in signs. So that's why I took a negative 2 value here and not any other value. And from 0.05 till 0.08 seconds, this entire horizontal line, your gradient is what? Change in B over change in T is what? 0. So your EMF will become 0. Okay, so let's place it here. Let's place a 0 value here. Something like this. Like this, and let's stretch these lines like this. And like this. This will get you how many marks? I guess this was a 4 marks. So this will get you a 4 on 4. Let's move on to the next question. Define magnetic flux density. Okay, so magnetic flux density is represented with a symbol of what? B. And do you remember a formula for B? B is equals to force I over L. So how will we define it? Magnetic flux density is the force per unit length per unit current, per unit length per unit current, or you can say per unit ampere as well, given that this is the force per unit length per unit current, given that the length of the wire is perpendicular to the magnetic field, is perpendicular to the magnetic field. Simple as that. Now let's move on to part B. Electrons are moving in a vacuum with a speed of this. Okay. The electrons enter a uniform magnetic field of flux density this. Okay. Figure 6.1 shows the path of the electrons. Okay. We have the B, we have the velocity. Okay. Let's see what is being asked here. State the direction of the magnetic field. Okay. You have to state the direction of magnetic field. Now this will use Fleming's left hand rule. Okay. So the electrons are pointing towards the right. What will be your direction of current? Towards the left. Okay. Where is your force pointing? Downwards. Where will your magnetic field point? Inward. This is how you will place your hand, and your magnetic field will point into the page. State the direction of the magnetic field into the page. Into the page. Simple as that. Let's further move ahead. Show that the magnitude of the force exerted is this. So how do we calculate the force on any moving charged particle? Yes, do you remember how to calculate the force on any moving charged particle? BQV. What is B equal to? B is equals to 4.8 millitesla. Let's put it here. 4.8 into 10 raised to the power of minus 3. What is the charge of electron? 1.6 into 10 raised to the power of minus 19. What is the velocity of electrons? Yes, 1.7 into 10 raised to the power of 7. 1.7 into 10 raised to the power of 7. Your force comes out to be 1.3 into 10 raised to the power of minus 14 Newton. Simple as that. On figure 6.1, draw an arrow to indicate the direction of the centripetal acceleration of the electrons where it enters the magnetic field at point X. Okay. You have to show the direction of centripetal acceleration at point X. So where will the electrons accelerate? Something like this. Something like this, downwards. This is your direction of centripetal acceleration. I guess we have to mark an arrow. Yes. Draw an arrow. Yes, I have done that. Use the information in B1 to calculate the distance D. Okay. Between the path of the electron entering the magnetic field and the path of the electrons leaving it. So what is this distance D? This entire distance D. How can we calculate this? How can we calculate this? We know that the centripetal force here is equals to the magnetic force. We know that the centripetal force is equals to the magnetic force in this case. So let's apply the same logic here. I guess we have discussed this in an earlier question as well. Centripetal force is equals to magnetic force. What is the formula for centripetal force? mv square over r. What is the formula for magnetic force? bqv. V and V gets cancelled out. Okay, what do we have to calculate? R. Let's calculate mv divided by bq is equals to r. What is the mass of an electron? The mass of an electron, it is given in the data booklet, that is equals to 9.11 into 10 raised to the power of minus 31 kg. If you don't remember this, kindly refer to the data booklet. 9.11 into 10 raised to the power of minus 31 kg. What is your velocity here? Yes, velocity is 1.7 into 10 raised to the power of 7. 1.7 into 10 raised to the power of 7. What is B? Yes, what is B here? 4.8 into 10 raised to the power of minus 3. 4.8 into 10 raised to the power of minus 3. And what is your charge of an electron? 1.6 into 10 raised to the power of minus 19. What does your R comes out to be? What does your R comes out to be? 0.02 meters. Okay. But if you focus closely on the question, you had to calculate D and not R. What is R? R is half of D. This is R. If you take an other R, R plus R will be equal to D. So D is equals to 2R. D will be equal to what? 2 into 0.02. This is equals to 0.04 meters. So let's write D as 0.04 meters. 0.04 meters. Okay. The electrons in B are replaced with positrons. Okay, wow, that's good. Positrons have a positive charge. Okay. That are moving with a speed of this. Okay, 3.4 into 10 raised to the power of 7. The positrons enter the magnetic field at point X on figure 6.1. Okay. On figure 6.1, draw a line to show the path of the positron through the magnetic field. Okay. So let's compare electrons and positrons. Electrons and positrons. Let's do a comparison. So first of all, the first thing that you must know is electrons are what? Electrons are negatively charged. Positrons are positively charged. Now what will this do? What will this do? Your current will now start pointing towards the right for the case of positrons. Your current will start to point towards the right for the case of positrons. Let me do it here. Okay. And your magnetic field is inward. So where will your force point now? Your force will point upward. So instead of deflecting downwards, positrons will deflect upwards. Okay, this is the first change. This is the first change that will happen. Okay. Secondly, if you see here, your radius used to depend on what? mv over bq. Okay. Both of them have the same mass. Both of them have the same b and b. What is changing? The velocity for electron was 1.7 into 10 raised to the power 7. That is v. However, the velocity for positron is what? 3.4 into 10 raised to the power of 7. That is 2v. So if your velocity v changes to 2v, what will happen to your radius? Your radius will also double. Your radius will also go from r to 2r. So how will you draw the deflection of positron here? First of all, it will be upward and it will cover a larger area compared to this electron. Something like this. So let's further move ahead to the next question. Okay. A heavy aluminum disc, okay, has a radius of 0.36 meters, okay. The disc rotates with the wheels of a vehicle and forms part of an electromagnetic braking system on the vehicle, okay. In order to activate the braking system, a uniform magnetic field of flux density 0.17, this is your B, okay, is switched on. This magnetic field is perpendicular to the plane of rotation of the disc as shown in figure 8.1, 6.1, sorry, okay. Define magnetic flux. Okay, you have to define what? Phi. You have to define phi. So phi is equals to what? Magnetic flux. Magnetic flux is the product of magnetic flux density is the product of magnetic flux density and area perpendicular to the magnetic field. Area perpendicular to the magnetic field. Simple definition for magnetic flux. Let's move on to the next one. Calculate the magnetic flux through the disk. Give a unit for your answer. Okay, so we have to calculate phi. Phi is equals to BA. What is your B here? 0.17. Okay. What will be your area here? Since this is a circular coil and it has a radius of 0.36, what will be your area? Pi r, that is 0.36 square. Your phi comes out to be what? Can anyone calculate? Your magnetic flux comes out to be 6.9 into 10 raised to the power of minus 2. Always remember the units for phi are Weber's WP. Chalo, let's further move ahead. The disk is rotating at a rate of 25 revolutions per second. Okay, this becomes your frequency. Okay. Calculate the magnitude of electromotive force induced between the axle and the rim of the disc. Okay, you have to calculate EMF. What used to be EMF? EMF used to be change in phi over change in t. You have already calculated change in phi. You have already calculated the change in phi for one complete rotation, that is 6.9 into 10 raised to the power of minus 2. How will you calculate the time for one complete rotation? 25 revolutions happen in 1 second. Okay. So one revolution will happen in how many seconds? X. Cross multiply it. X is equals to 1 over 25. Okay. So your change in phi is what? 6.9 into 10 raised to the power of minus 2 divided by 1 over 25. Your EMF comes out to be what? Yes, your EMF comes out to be 1.7 volts. Okay. Let's see part C. The axle and the rim are connected into an external circuit that enables the energy of the rotation of the disk to be stored for future use. Okay. The direction of rotation is shown in figure 6.1. Okay. The direction of rotation is shown in figure 6.1. Use Lenz's law of electromagnetic induction, okay, to determine whether the current in the disk is from rim to axle or from axle to the rim. Okay. Let's see this. Okay, so if you see here, initially the force is acting upwards. Okay. If this force is initially acting upwards, this is the force that you will provide. Okay. But due to the magnetic field and due to the current, another force will be generated. And this force will oppose the motion of the initial force. So when you will apply Fleming's left hand rule, your thumb will point downward, your magnetic field finger will point towards the right, and then you will get the direction of current as inward, like this. So your current is from the rim to the axle, from the rim towards the axle. You can say that according to Lenz's law, according to Lenz's law, induced EMF always flows in a direction to oppose the change causing it, to oppose the change causing it. Hence, the force produced, hence the force induced due to the current, is acting downwards, And if the force produced is acting downwards, what will you say? Apply Fleming's left hand rule to get the direction of current, to get the direction of current from. So you can write that the direction of current is from the rim to axle, full stop. Let's move on to the next question. Let's move on to the next question. State what is meant by a magnetic field. What is meant by a magnetic field? A region around a magnet where other magnets or current carrying conductors, other magnets or current carrying conductors experience a force. Okay. A region around a magnet where other magnets or current carrying conductors experience a force. Okay. A long straight wire P carries a current into the page. Okay. So current is going into the page as shown in figure 6.1. Okay. On figure 6.1, draw four field lines. Okay, now this is a task. You have to draw four field lines to represent the magnetic field around wire P due to current in the wire P. Okay. So this is why I would suggest you guys to take compasses in your A2 physics exam. You will draw circles like these, and the distance between these circles will keep on increasing. Something like this will be a challenge. Okay, so let's draw two more field lines. Something like this. I hope I don't mess up. Yeah, something like this, and the last circle as well. Something like this. Okay. And all of these will have a clockwise direction. Why? Because magnetic field is going into the page like this. So this simple question basically gives you 3 marks in A2 level. So these questions make me laugh because this is just clockwise direction में four circles and you are good to go with your 3 marks. Let's further move ahead. A second long straight wire Q carrying a current of 5 ampere out of the page. Okay, this is carrying current out of the page is placed parallel to the wire B as shown in figure 6.2. So right off the bat, what I can think, this is going into the page, this is going out of the page. Both will repel each other. Okay. The flux density of magnetic field at Q due to the current in wire P is this. Okay, we have B as well. Okay. Determine the force per unit length exerted on wire Q by wire P. Okay. We have to calculate the force per unit length on wire Q by wire P. So F is equals to BIL. Divide L here. Force L is equals to BI. Now B will be what? 2.6 into 10 raised to the power of minus 3. And you have to calculate the force per unit length exerted on wire Q by wire P. So what will be your current key value that you will be choosing here? Your current key value will be the current in wire P. 5 ampere. This comes out to be what? Yes, can anyone tell me what this force per unit length comes out to be? 0.013 Newton meter minus 1. Simple as that. Let's further move ahead. State the direction of the force exerted on wire Q by wire P. Okay, we have to state the direction of force exerted on wire Q by wire P. Okay, so what will be the direction of force that wire Q exerts on wire P? Basically, it will repel the force. It will repel the force. Both of these wires will repel each other. Both of these wires will repel each other. So maybe a force like this. And this is what we had to draw. Okay, we had to draw a force on wire Q by wire P. Okay. Let's say the roles were reversed. Let's say we had to draw a force on wire B. Then this will be the force. Both of them will repel each other. Okay. Uh, you have to state the direction. Okay. So you will say towards the right. Let's move on to part 3. The magnetic flux density of the magnetic field at wire P due to the current in wire Q is this. Okay. This is the magnetic field, magnetic flux density B at wire P due to wire Q. Okay. Calculate the magnitude of the current in wire P. Calculate the magnitude of current in wire P. Okay. So, according to Newton's law, you must know that the force that wire P exerts on Q is equals to the force that wire Q exerts on P. According to Newton's third law, both these blue forces, the force that wire Q exerts on P and the force that wire P exerts on Q, will be equal to each other and opposite in directions. Okay, so have I calculated the force per unit length? Have I calculated the force per unit length for FP? Yes, that is 0.013. So what I can do here is, let's first of all let's divide the equation by length, because both of them have the equal length. So FP over L is equals to FQ over L. Have I already calculated FP over L? Yes, this was FP over L. This was FP over L. What was this coming out to be? 0.013. 0.013. Let's place it here. 0.013. What was your force in Q? Uh, you don't know about that. Okay. So let's place it like this. Force Q over L. Okay. Now, if you remember one thing, force over L is equals to what? B into I. So I can replace it here. 0.013 is equals to BQ into IQ. Okay. What is your magnetic flux density here? 1.5 millitesla. 0.013 is equals to 1.5 into 10 raised to the power of minus 3. Can I calculate the current in wire Q? Yes, you surely can. Current is equals to 0.013 divided by 1.5 into 10 raised to the power of minus 3. This comes out to be what? Current in Q comes out to be what? 8.7 ampere. Simple as that. Let's further move ahead. You can also check your answers. So, a Hall probe is placed in a magnetic field. The Hall voltage is initially zero. The Hall probe is rotated to a new position in the magnetic field. The Hall voltage is now maximum. Explain these observations. So, what can we say? Initially, the Hall probe, the Hall probe is parallel to what? Parallel to magnetic field. Hence, reading is 0. However, however, at the maximum reading, at the maximum reading, the whole probe is perpendicular to the magnetic field, perpendicular to the magnetic field. Simple as that. Nothing complicated here. Okay, let's move on to part B. The formula for calculating Hall's voltage as measured by a Hall probe is this. Okay, this is the formula to calculate Hall's voltage. Bi divided by NTQ. Okay. Table 6.1 shows the values of N for two materials. Explain the meaning of N. What used to be N? The number of electrons per unit volume. Okay. Explain why Hall probe is made from silicon rather than copper. Okay, let's see that. Can you see silicon have a lower number of N? Can you see silicon has a value of N that is 10 raised to the power of 15? Its N is less, hence its Hall's voltage will be greater. And if the Hall's voltage is greater, it is easier to measure. The N of silicon is less, leading to a higher Holes voltage leading to a higher holes voltage, and hence easier to measure, and hence easier to measure. Simple as that. Let's further move ahead. A Hall probe gives a maximum reading of 24 millivolts when placed in a uniform magnetic flux density of 32 millitesla. Okay, so your whole probe reading, holes voltage reading is 24 millivolts. Let me write it here. If your magnetic flux density is 32 millitesla, okay. The same Hall probe is then placed in a magnetic field of fixed direction and varying magnetic flux density. Okay, the Hall probe is fixed in a position so that the angle between the Hall probe and the magnetic field is same as when the Hall voltage was 24 millivolts. Okay, the variation of Hall's voltage on the Hall probe from time t is equal to 0 till 8.6 seconds is shown in figure 6.1. Okay. From 0 to 8.6 seconds, you have the variation of Hall's voltage. Okay. If you can see here, I notice a very interesting thing here. If you see here, I notice a very interesting thing here. Your maximum Hall's voltage here is 36 millivolts. Okay. Something is going fishy here. If your maximum Hall's voltage is 36 millivolts, what will be your maximum magnetic flux density? Can you cross multiply and calculate it? Yes. 36 into 32 divided by 24 is equals to your x. Let's calculate this. 36 into 32 divided by 24, this comes out to be 48. 48 millitesla is your maximum magnetic flux density for this scenario, for the scenario shown in graph. Okay. The coil has 780 turns, the diameter of this, okay. You have to calculate the maximum EMF. Okay, you have to calculate the maximum EMF. Okay, what used to be EMF? EMF used to be NA into change in B over change in T. Okay. So first of all, from this graph, highlight the maximum gradient wala point. This line has the maximum gradient because it is the most steep line. Positive and negative doesn't matter for now. What is your value of n? 780. What will be your area? Pi into this is diameter. So radius will become what? 1.8 centimeters. So pi into radius, that is 1.8 into 10 raised to the power of minus 2 whole square. What will be your change in B here? What will be your change in B here? If you see here, initially your Hall's voltage is at a maximum value of 36. And at a value of 36, your B is 48. Then your Hall's voltage drops to 0. So if your Hall's voltage is 0, your magnetic flux density will also be 0. So what is your change in B? Your change in B is 48 minus 0 into 10 raised to the power of minus 3. What is your change in time? Initially, your time was this thing, that is 7.2. Then your time became this, that is 8.6. From 7.2 to 8.6, how much time this is? 1.4. Can you calculate the EMF? Yes. Can you calculate the EMF induced here? Yes, it is pretty easy to calculate. You have to just put in the values in the calculator. The EMF comes out to be 0.027 volts. Simple as that. Let's move on to the next question. Move on to this question. Define the term Tesla. So Tesla is the unit of what? Tesla T is a unit of what? Tesla T is the unit of magnetic flux density. Okay, so how are we going to define Tesla? Very easy. Tesla is equals to Newton per meter per ampere for a current carrying conductor perpendicular to the magnetic field. Perpendicular to the magnetic field. Very simple definition. Perpendicular to the magnetic field. Now let's see part B. Let's observe part B. A stiff metal wire is used to form a rectangular frame 8 centimeter by 6 centimeter. Okay. The frame is open at the top and is suspended from a sensitive Newton meter. Okay. It is open at the top and is suspended from a sensitive Newton meter. Okay. As shown in figure 8.1. Okay. The open ends of the frame are connected to a power supply so that there is a current of 5 ampere in the frame in the direction shown. Okay, there is a 5 ampere current flowing in the frame like this. Okay. The frame is slowly lowered into a magnetic field of flux density B. Okay. So that all of the side PQ is in the field. Okay, side PQ is in the field. Okay. The magnetic field lines are horizontal and at an angle of 50 degree to the PQ. Okay, as shown in figure 8.2. Okay. So these are your magnetic field lines. This is your line. This is your wire PQ. Okay. When side PQ of the wire frame enters the magnetic field, the reading on the Newton meter changes by 1 millinewton. Okay. Determine the magnetic flux density B in millitesla. Okay, you have to determine B. Okay, so for magnetic flux density at an angle, see the wire is at an angle. It is not completely perpendicular to the magnetic field. So whenever the wires used to be at an angle, your magnetic flux density used to be equal to what? F divided by IL sine of theta. What is your force here? 1 into 10 raised to the power of minus 3. Okay, 1 into 10 raised to the power of minus 3. What is your current here? 5. What is your length here? Yes, can you tell me what is the length here? The length here is 6 centimeter. Okay, into sine of, one more thing we are missing here. This length is 6 centimeters. So we will have to convert it into meters. So 6 into 10 raised to the power of minus 2 multiplied by sine of what? Multiplied by sine of 50. Okay, let's place it here. Your magnetic flux density comes out to be what? Your magnetic flux density comes out to be 4.4 millitesla. Okay. State with a reason whether the change in the Newton, in the reading on the Newton meter is an increase or a decrease. Okay. So let's start. So basically your magnetic field is going into the page. Your magnetic field is going into the page. So your first finger will point inward. Let's apply Fleming's left hand rule. Your first finger will point inward. Your current will point towards the right. Okay. Your magnetic field is inward, current is towards the right. Where will your force point? Your force will point upward. Your force will point upward. If your force is pointing upward, this change in reading will be a decrease. How do I know that? Okay. See, initially there will be only weight acting downward, and this will be shown on the Newton meter. But now you have an upward force. Now you have an upward force. This upward force will decrease the reading on the Newton meter. So you can write it here. According to Fleming's left hand rule, Fleming's left hand rule, the coil experiences an upward force. An upward force. This causes the reading on Newton meter to decrease. This causes the reading on Newton meter to decrease. Simple as that. the frame is lowered further. ठीक है, frame को we have lowered it further so that the vertical sides start to enter the magnetic field. Suggest what effect will this have on the frame? Okay. Now the vertical sides are also inside the magnetic field. What will this do? This will cause a force on these vertical sides as well. And once you have a force on the vertical sides, the coil will start to rotate. You can write it here. The coil will start to rotate. Simple as that. Let's further move ahead. Define magnetic flux density. Again, we have to define B. I guess we have done it earlier. In the notes as well, you have the definition for this. And you can scroll up the video and you will find it in the previous questions as well. Electrons each of mass m and charge q are accelerated from rest, okay, in a vacuum through a potential difference v, okay. Drive an expression in terms of mqv for the final speed v of the electrons. Explain your working, okay. So what will we say? What will we say? Electric potential energy is equals to your kinetic energy. What was electric potential energy का formula? Charge into the electric potential. What was kinetic energy का formula? 1 upon 2 mv square. Now you have to do what? You have to show speed of the electrons, okay, as the subject. So multiply 2 to the other side. 2qv divided by m under root is equals to your velocity. So this is how you derive velocity's expression. The accelerated electrons in B are injected at point S, okay, into a region of uniform magnetic field of flux density B as illustrated in 8.1, okay. This is a uniform region of flux density B. Path of electrons has a radius of r, and yeah, that's all we are given here. Show that the specific charge of the electrons is defined by this expression, okay. So if you observe here, what is happening? The magnetic force is equals to what? Is equals to the centripetal force. If you closely observe here, the centripetal force is equals to the magnetic force. Okay, once we have equated the centripetal force to the magnetic force, what we will do? We will place the formula for centripetal force as mv square over r and for magnetic force as bqv. What will be the next thing? We will cancel out these velocities. Okay. Now we have to make q over m as the subject. So let's isolate q over m. Let's keep q here divided by m. This equals to what? V over rb. Now you will notice a very strange thing here. In the final answer, you have your voltages or electric potential. In your answer, you have velocity. What should we do here? Now we can recall the earlier part and we know that velocity is equals to what? 2qv divided by m. Let's write it here. Velocity is equals to under root 2qv over m. Let's substitute it here. Q over m is equals to under root 2qv over m rb. Now let's take squares on both sides. Take square on both sides. Okay, let's do that. This becomes what? Q square m square is equals to 2qv divided by m r square and b square. Is anything getting cancelled out? Yes. This q square will get cancelled out with this q. This m square will get cancelled out with this m. What is your final answer? Q over m is equals to 2v over r square b square. That is similar to the thing given in our question. So we have proved that. Let's further move ahead. Electrons are accelerated through a potential difference of this. Electrons are injected normally into the magnetic field. This is your B. The radius r is this use this information to calculate the value of the specific charge. Q over m value we have to calculate for an electron. What was the formula? Q over m is equals to 2V over R square Bu square. What is your voltage value? 230. What is your radius value? 0.14 whole square. What is your B value? 0.38 into 10 raised to the power of minus 3 whole square. Can you calculate the value of Q over M? Yes, it comes out to be what? 1.6 into 10 raised to the power of 11. Simple as that. Suggest why the arrangement outlined in 2. Okay, why the arrangement outlined in 2 using the same values of B and V is not practical for the determination of the specific charge of alpha particles. Okay. Why can't we use this same arrangement for alpha particles? Okay. Let's calculate the specific charge for alpha particles and let's calculate the specific charge of electrons. Okay. We have been using this apparatus for electrons. Okay. As you can see here. The charge on an alpha particle is 2 into 1.6 into 10 raised to the power of minus 19. And the mass is 4 into 1.66 into 10 raised to the power of minus 27. However, for an electron, the charge is what? The charge is 1.6 into 10 raised to the power of minus 19 divided by 9.11 into 10 raised to the power of minus 31. Let's put these values in the calculator and calculate the answer. 2 into 1.6 into 10 raised to the power of minus 19 divided by 4 into 1.66 into 10 raised to the power of minus 27. This gives you a value of 4.8. This gives you a value of 4.8 into 10 raised to the power of 7. However, for an electron, if I do that, 1.6 into 10 raised to the power of minus 19 divided by, if I put it here, 9.11 into 10 raised to the power of minus 31. This comes out to be what? 1.75 into 10 raised to the power of 11. Can you see the Q over M for alpha particles is small? Yeah, what will that do? What will that do? If this value Q over M gets small, what will happen? Your radius will increase. And hence, you can't accommodate alpha particles in this smaller circle. So, what will you write? The Q over M for alpha particles is small. Hence they have a larger radius. Hence they have a larger radius, making it difficult, making it impossible for making it impossible or difficult to determine, making it difficult to determine specific charge of alpha particles using this apparatus. Using this apparatus. Simple as that. As you can see here, this will be the answer in the marking scheme as well, I think. Yes. So, yeah. Let's further move ahead. State two situations in which a charged particle in a magnetic field does not experience a force when the charge is stationary. When the charge is stationary. And what could be the second condition? Yes. Do you guys remember? When the charge is parallel to the magnetic field, is parallel to the magnetic field. Simple as that. To the magnetic field. Okay. Let's do part B. A loosely coiled metal spring is suspended from a fixed point as shown in figure 9.1. Okay. Electric connections are made to the ends of the spring. Okay. Electric connections are made to the end of the spring here and here. Okay. The length of the spring is measured before the switch is closed and then again after the switch is closed. I think this is a similar question that we have done earlier. When the switch is closed, the magnetic field is set up around each of the coil in the spring. Okay. By reference to these magnetic fields, explain why there is a change in length of the spring. State whether the spring extends or contracts. I think we have done a similar question earlier. So I will just write key points here. You will write that current in each coil generates magnetic field, magnetic field. These magnetic fields, these magnetic fields interact with currents in other coil, with currents in the other coil, in the other coil. This generates, this generates attractive force and attractive force. Why? Since currents are traveling in the same direction. Since currents are traveling in the same direction. Traveling in the same direction. And what will be your fourth point? Your fourth point will be spring contracts. Simple as that. Spring contracts. Okay. So you can write it here for the 4 marks. Okay. Okay, with the switch in B closed, the small mass on the free end of the spring is now made to oscillate vertically. Okay. Use the principles of electromagnetic induction to explain why small fluctuations in the current in the spring are found to occur. Okay. So, as the mass is oscillating, what do you think will happen? As the mass oscillates, the as the mass oscillates, there is a change in magnetic flux. As the mass oscillates, there is a change in there is a change in magnetic flux. Okay, what will happen due to this? This changing magnetic flux, this changing magnetic flux, magnetic flux induces EMF. Okay, this changing EMF, changing EMF causes the current in the spring to fluctuate. This changing EMF causes the current in the spring to fluctuate. To fluctuate. Simple as that. Let's move on to the next question. Okay, let's move on to this question. Define magnetic flux linkage. You have to define phi again. I guess we have done it earlier. You can scroll back in the video and see that. A solenoid has a diameter of this. Okay, this is your diameter. Your radius will become what? 3 centimeter. Okay, the number of turns are 540. Okay, are placed in a uniform magnetic field as shown in figure 9.1. Okay, now let's see this graph. The variation with time t of the magnetic flux density as shown in figure 9.2. This is B versus T graph. Okay. Calculate the maximum magnitude of the induced EMF. Okay, you have to calculate the maximum of induced EMF. So EMF is equals to what? NA into change in phi over, NA into change in B over change in T. Okay. What is your N? What is your N? 540. Okay. What is your A? What is your area? It is 3 centimeter. We can calculate that this will be pi 3 into 10 minus 2 whole square into what is your change in B over change in T. Okay, we have to calculate the maximum magnitude. Again, these are very similar questions. Maximum EMF we have to calculate. So we will put in the maximum value of change in B over change in T. Where is the maximum steep in this graph? Here, this line. Okay, how can I calculate the gradient here? Let's take 2 points here. Let's say this is the first point, that is at a x value of 6, y value of 250. Then we have this point that is at an x value of 7.2, y value of 0. Okay. So can we calculate the gradient here? Yes, minus 250 divided by 1.2 into 10 raised to the power of minus 3 on the y values, because we have millitesla. So can you calculate this gradient? Yes, sure. 250 into 10 raised to the power of minus 3. Okay. Divided by 1.2. The gradient comes out to be 5 divided by 24. The gradient comes out to be 5 divided by 24. Either you include the minus sign or exclude it, it doesn't matter. 5 divided by 24. Calculate your answer. Your answer for EMF comes out to be what? Yes. Can anyone tell me the answer? What does the answer for EMF comes out to be? Your answer for EMF comes out to be what? 0.32. 0.32 volts. Let's move on to part C. A thin copper sheet X is supported on a rigid rod so that it hangs between the poles of a magnet as shown in figure 9.3. Okay. This is a copper sheet. This is hanging between the poles of the magnet. Okay. Sheet X is displaced to one side and then released so that it oscillates. Okay. A motion sensor is used to record the displacements of X. Okay. A second thin copper sheet Y replaces X. Okay, now we have replaced Y with X. Okay. Sheet Y has the same overall dimension as X, but it is cut into shape as shown in figure 9.4. Okay, this is the shape of sheet Y. Okay. The motion sensor is again used to record the displacements. The graph in figure 9.1 shows the variation with time t of the displacement S of each copper sheet. Okay. So one of these graphs is for X plate and one of these graphs is for Y plate. Okay. State the name of the phenomena illustrated by the gradual reduction in the amplitude of the dash line. Let's see where is the okay. What is happening here? What does this decrease in amplitude show you? Light damping. Light damping. Okay. Now, deduce which copper sheet, okay, which copper sheet is represented by the dashed lines. Explain your answer using the principles of electromagnetic induction. Okay. Which of these sheets is represented by the dashed line? We have to explain and using electromagnetic induction's law. Okay. So first and foremost, whenever these sheets oscillate, as you can see, the arrows are already made, these black arrows, these arrows that I've highlighted in yellow. Whenever the sheet oscillates between the magnetic fields, what happens? What happens? You can write it here. The sheets of copper cut the magnetic flux, inducing EMF in the sheets, Simple as that. This induced EMF, always remember, this induced EMF leads to what? Leads to current in the sheets. Always remember, whenever you have induced EMF, it will lead up to what? Current. Okay. This current causes what? Beta, current se kya hoga? Let me erase this. This current causes what? This current causes heating effect and energy is wasted. Now, If you see sheet X has a larger area. So a larger current will flow through sheet X. Hence, sheet X be will have a larger heating effect and there will be larger amount of heat dissipated during sheet X. However, sheet Y has a smaller area. Lesser current will flow through sheet Y and lesser heating effect will take place through sheet Y. So you can write it here. You can write it here that this shaded region, shaded graph you can say, will be for X. Why? Because X has a larger area, X will be supplied with a greater amount of current, hence larger amount of energy will be dissipated, hence it is a lower amplitude. Dash line will be your X plate. You can write it here. Dash line, I think we have to tell about the dash line. Yes, dash line is plate X, is sheet X, you can say, is sheet X because sheet X has a larger area, has a larger area. This allows for larger current, and larger current will cause more heating effect. More heating effect will result in what? More heating effect will result in higher, yeah, more dissipation, yeah, more wastage of heat, I guess. More wastage of energy. More wastage of energy. Simple as that. Let's move on to our last question. Okay, define the term Tesla. Again, we have done that, and I guess you can copy it from the previous questions in the video. A magnet produces a uniform magnetic field, okay, of flux density B in the space between its poles, okay. A rigid wire carrying a current is balanced on the pivot. Part PQLM of the wire is between the poles. Okay, PQLM is between the poles of the magnet as illustrated in figure 8.1. Okay. The wire is balanced horizontally by a means of a small weight. This is the small weight attached here. Okay, that's perfect. The section of the wire between the poles of the magnet is shown in figure 8.2. That's very helpful from the examiner. He has given us the section that is between the magnets. Okay. Explain why section QL of the wire gives rise to a moment about the pivot. Okay. So section QL will have current flowing like this. Okay. This will be the magnetic field. So let's apply Fleming's left hand rule. Fleming's left hand rule here. Let's apply Fleming's left hand rule here. Your magnetic field is like this. Your current is into the page. What will be your force like? Your force will be pointing upward. Your force will be pointing upward. Let's mark that force in green. Let's mark that force in green. Something like this. Okay. You will have a upward force here like this. This upward force is what? If I take you to the original diagram, if I have an upward force here, this is what? This force will cause a moment about this pivot P. Why? Because it is not passing through the pivot. It is perpendicular, you can say. So how will you phrase this answer? How will you phrase this answer? First of all, you will say according to Fleming's left hand rule, Fleming's left hand rule, left hand rule, there is a force, there is a vertical force, you can say, in section QL. And this force, this force does not, this force does not pass through the pivot, pass through the pivot. Hence, it generates what? It generates a moment. Simple as that. Section PQ and LM of the wire do not affect the equilibrium of the wire. Why? Section PQ and LM do not affect the equilibrium of the wire. Although there will be forces acting on PQ and LM as well. Although there will be forces acting on PQ and LM as well. But if you notice, these forces will be passing through the pivot. These forces F will be passing through the pivot. Hence, they do not affect the equilibrium. You can again write here according to Fleming's left hand rule. Fleming's left hand rule. Left hand rule. Forces act on PQ and LM. But these forces pass through the pivot. Pass through the pivot. Hence, no moment generated and they do not affect the equilibrium. And they do not affect the equilibrium. Affect the equilibrium. Simple as that. Let's further move ahead. Okay. Section QL of the wire has a length of this. Okay, this is the length of section QL. Okay. The perpendicular distance of QL from the pivot is this. Okay. This is the distance of the pivot from the wire QL. Okay. When the current in the wire is this, W is moved through a distance of this along with the wire in order to restore equilibrium. The mass of W is this. Show that the change in moment of W is this. So moment is equals to what? Weight into the distance moved. What is your weight? 1.3 into 10 raised to the power of minus 4 multiplied by 9.81 multiplied by what is the distance? 2.6 centimeters. So 2.6 into 10 raised to the power of minus 2. What will this moment come out to be? 3.3 into 10 raised to the power of minus 5 Newton meter. Okay. Let's further move ahead. Use this information. Okay, we have to use this information to determine the magnetic flux density between the poles of the magnet. Okay. We know that moment is equals to force into length. And we also know that force into, okay, one thing here that will get you confused is, let's put this as moment is equals to force into distance from the pivot. Okay. How will I calculate this force? How will I calculate? Okay, let me erase these two other green forces. How will I calculate this force on QL? Very easy. I will apply the formula BIL. BIL. And this D is the distance from the pivot of section QL. Okay, do I have the moment? Yes, I have already calculated in the previous question. 3.3 into 10 raised to the power of minus 5. What is my magnetic flux density? I have to calculate. What was my current in the wire QL? 1.2 ampere. Okay, let's put 1.2 here. What was my length of the wire? My length of the wire was 0.85 centimeter. Okay, 0.85 into 10 raised to the power of minus 2 divided by the distance from the pivot. That was what? That was 5.6 centimeter. Let's do that. 5.6 into 10 raised to the power of minus 2. Your answer comes out to be what? Your answer for B comes out to be what? Can you calculate it? It comes out to be 0.058 as your answer. This marks the end of topical questions for electromagnetism. If you have any questions, you can ask me in the comments. And this PDF is attached in the description below. Thank you for watching.